Welcome back, everyone. I'm Akash Joshi. I'm the Operations Research Guru, and today we're going to be talking about the standard form of linear programs. Now, there is a standard form of linear programs so that all linear programs look the same so that computers can easily solve the linear programs and they don't have to navigate the intricacies of how you formed your linear program. So, I'm going to teach you the standard form and how to standardize your linear program. Okay, so let's talk about the standard form first. So here's the standard form, and here are the main three rules. Now, some people can break these rules up down further, but generally these are three rules. So the first rule is that all variables, especially decision variables, have to be positive. The second rule is all the values on the right-hand side are positive. The third rule is that all constraints or equalities other than the non-negativity constraints must um they must be equal. Wait, let me repeat that. All constraints have to be equalities other than the non-negativity constraints. Okay, now that I've gone over the rules, let's see if we can perform standardization on a linear program. Okay, let's look at our problem. We want to use the simplex method to solve the linear program, but the linear program is not standardized, so the computer will not accept it and it returns an error because it cannot perform the simplex method. Okay, so we have our program mathematical model right here. It's a minimization function, and we have some constraints right here, and x1 is negative. So let's perform step one. So step one is to ensure that all variables are positive. So right off the bat, we see that x1 is going to be negative. So how do we make it positive? We simply flip the sign of all of the x1s, and then we change x1 to be greater than 0. That way, all of these values will still be the same because we are adding a negative sign and making x1 positive, because a positive times a negative is the same thing as a negative times a positive. But if you notice, we don't have a constraint, a non-negativity constraint for x2. x2 can still be negative, so we have to make sure that x2 stays positive. How do we do that? Let's see. All right. So um we basically, instead of having an x2, we substitute x2 for x2 minus x3, and keep in mind that this x2 is different than this x2 now because we are defining it differently. So if we define x2 and x3 to be non-negative, then x2 minus x3 can still be positive or negative, but both variables have to be positive. And the way that x2 minus x3 can still be negative, it would be if x3 was greater than x2. So yeah, let me repeat that one more time. So over here we have 7x2, and to keep the linear program the exact same, but we're only standardizing it, but we want the linear program to be exactly the same. That means x2 should be able to be negative, but because linear programs have to be standardized and they can't be negative, we have to replace x2 with a different x2 minus x3. And once we replace it, we can say that both of them are greater than 0 because um because when you standardize the linear program, there are all variables have to be positive. However, this x2 minus x3 can still be negative if x3 is greater than greater than x2. Okay, that way this value stays the same as this value, and then we simply just substitute it in for all of the other x2s, and then we can add this non-negativity constraints for all three variables. X1 is greater than 0, x2 is greater than or equal to 0, and x3 is greater than or equal to 0. So when we perform this linearization task, this way the value of x2 can still be negative, even if, I mean, not even if, the value of x2 can still be negative, especially if x3 is greater than x2. All right. So our second step is to make all the values on the right positive. This is pretty simple. We see a negative 8 here. Everything else is positive, this 5 and these 3 zeros. And on the right-hand side, it means the right-hand side of the equality or inequality. So the right-hand side of this inequality would be 5. So yeah, so if you notice, there's only one negative, which is negative 8, and we want to make that positive. And if you've taken algebra, you know that we can just make this positive, flip the sign, and multiply this side by -1. That way all of these signs change. Okay, so now that we have completed step 2, we are ready to move on to step 3. We are converting the inequalities to equalities. So if you take an algebra, you probably know that it's like they don't probably teach you how to convert inequalities to equalities, but we are going to use something called a slack variable. So if you notice over here, we are saying that this left-hand side is greater than the right-hand side. So if the left-hand side is greater than the right-hand side, then we must subtract something from the left-hand side for it to be equal to the right-hand side. What are we subtracting? We're subtracting x4, which is our slack variable. And if we say x4 is positive, which we have over here, that way, when this is bigger than 5, we are subtracting something from 5, something tiny from, not, sorry, let me repeat that. We are subtracting something from something that's bigger than 5 so that it equals 5. And we perform the same thing over here for this constraint. This value is greater than 8, so if we subtract something from it, hopefully we can find that something so that it equals exactly 8. So we are going to call these two slack variables x4 and x5, and we just treat them like any other variable. We're going to say that they're both positive because that's the standardization rule. Xi is greater than or equal to 0 for all of I, and I is defined as 1, 2, 3, 4, and 5. All right, that's it for today. But now you may input this formulation into the computer, which will perform the simplex method and give you the optimal solution because you changed up your mathematical modeling in order to standardize it so that the computer can understand it. Okay, thank you for watching. I'm Akash Joshi. Goodbye.